Greetings, physics fam. We are looking at our review practice quiz. We're in the work energy unit, so we're learning about work, kinetic energy, potential energy, which are both mechanical energy. We're looking at the conservation of energy, the idea that the beginning potential and kinetic energy combined, which is called the total mechanical energy, is equal to the object's final potential and kinetic energy combined. Also, don't forget the energy work theorem, the idea that when you do work on an object, you either change its potential energy or its kinetic energy, so you can set those equal to each other. But now that we've had the formal introductions, you know what time it is. Let's get to some problem solving. So, take a look. David pushes a shopping cart 45 meters from the door. So to me, that is giving me a distance. All right, not sure if I'm gonna need that, but I'm gonna write it down. And he's pushing at a constant speed with a horizontal force of 40 newtons. All right, so I'm given a force of 40 newtons. How much work does David do to overcome the force of friction? Fair enough. The question we're looking for to answer is work. So I have my givens already, right, in my guess method, and I have my unknown. And I think we already know the drill. We know that work is force times distance. So I think this is going to be a pretty straightforward problem. My work is going to be my force, which is 40 newtons, times my distance, which is going to be 45 meters. So work is 40 times 45, which ends up being about 1,800 joules. Perfect. Sounds like a good start to me. Let's move on to 1B. Would David be using more power in this scenario if he pushed the cart to the car in 3/4 the original time? Now remember, if it was 4/4, he'd be pushing it the same amount. If it was longer or bigger than 1 times greater, like 1.5 times greater, he'd be pushing longer. But since it's only 3/4 the time, it's less time. So if he's doing this work in less time, that means that it's going to be more powerful. So if it's less time, it's going to take more power. Remember, because power is work divided by time. If you divide by a smaller number, this answer for power gets bigger. So that's why 1B ends up being more powerful, because it takes less time. All right, I like that. Let's scroll up a little bit and let's look at 2A. 2A says a couple ice skating, one holding the other in the air, okay, are moving together at 5.15 meters per second. So to me, that tells me that's some type of velocity. Perfect. If Natasha and Boris, oh, I like that. That's actually the name of 2 villains in the Rocky and Bullwinkle old cartoons. Check it out if you haven't. But Natasha and Boris have a combined mass. All right, I'm going to get a mass here of 122.5 kilograms. I'm sure they're graceful. Those are given to me. I want to know what their kinetic energy is. So my unknown is going to be kinetic energy. Lucky for all of us, we know at the top of the page, kinetic energy is 1/2 times mass times velocity squared. Perfect. So this looks like just an equation I'm going to plug in and chug out. I'm solving for kinetic energy. There's my KE. I'm going to cut my mass in half, which is 122.5. And my velocity is 5.15. And I'm going to square that. All right. So don't forget that. Keep that in mind. If I put that in my calculator, and double check, make sure you are putting in your calculator as well. Don't forget to square that 5.15 first. That's important. Otherwise, sometimes if you throw it all together and then square at the end, you're going to get the wrong answer. But my kinetic energy ends up being about 1,624.5 joules. Don't forget the unit for energy is joules there. Also, reminder, question number 1's energy was, sorry, not energy, but units were in joules as well. Remember, work and energy go hand in hand because of the work energy theorem. That's why they're measured in the same units. Let's look at 2B. Boris and Natasha stop on the ice. All right, Boris and Natasha, Boris holds Natasha up in the air for 2.3 meters in the air. Fine, so that sounds like a height to me. Ooh, I wonder if this is going to be a potential energy problem. What would Natasha's potential's energy be if Boris's mass is 77 kilograms? All right, so we know that the mass from the previous problem here, combined they were 122.5 kilograms. So if I subtract out Boris's mass minus 77, that's going to tell me her mass, Natasha's mass. So when I do that and subtract, I end up with 45.5 kilograms for those two. Fine, those are my given. It looks like I want to know the potential energy. That's my unknown, so that's my PE. And as you know, and hopefully you're almost starting to memorize it, potential energy due to gravity is mass times gravity times height. So let's throw that in and get that problem answered. All right, my potential energy is going to equal the mass of Natasha, which is 45.5. Gravity's acceleration is 9.8 since we're on planet Earth. And the height is 2.3. Fine. I think we're just going to multiply across, right? 45.5 times 9.8 times 2.3. And my potential energy ends up being 1,025.57 joules. Again, energy is measured in joules, so we figured out her potential energy due to gravity. Awesome. I'm liking how we're doing. I'm liking where we're headed. Let's look at 2C now. 2C is asking, Boris accidentally drops Natasha on the ground. Oh, poor thing. Once Natasha hits the ice, what happens to her kinetic energy and where did it go? Yikes. This is a good question. All right, so we know at the top, Natasha's all potential energy, and then as she drops, it turns to kinetic. But the question is, what happens to her kinetic energy once she hits the ground? Obviously, she's going to hit the ground and eventually stop. So what does that mean? When she hits the ground, believe it or not, that kinetic energy is going to turn to work because she's going to exert a force on the ice. And believe it or not, that ice will move slightly, a small distance, but her falling on the ice will smash the ice just a little bit and create a distance. So believe it or not, she's transferring that kinetic energy and it's turning into work on the ice, which is going to leave a divot in the ice. So when you're answering that question, make sure you put that in your own words. Copying my little notes here aren't going to really help you out. But think about that. Energy work theorem shows that the kinetic energy converts to work. Glad we talked about that. That's an important concept that confuses people quite a bit. So let's get that done. All right. 3A is in the house. Let's do it. Geppetto, a 50-kilogram boy. So right away, I'm given 50 kilograms for a mass. He climbs a tree 10 meters high. So because of a height, I'm going to go with 10 meters there. He hides from his angry mother. Oh, poor Geppetto. How much work does Geppetto do in order to reach the top of the tree? Yikes. Okay, so first of all, we're given 50 kilograms and a height of 10 meters. Fine. The unknown is we want to know the work. But take a look. What is the equation for work? Work is force times distance. All right, so we could look at this a couple different ways. First of all, force times distance, you could say that the force exerted by the boy, since we know his mass, remember the weight of the boy is just his mass, 50 kilograms, times 9.8, right? Because if you take the force of gravity, that's the force really he's overcoming by climbing up the tree. So if we do the weight, which is 50 times 9.8, you end up getting about 490 newtons for your answer for force. All right, so now we can plug in for force. Let's do that. I'll do it in a different color. Force is going to be 490. This will be my S for substituting. And the distance he travels is 10 meters. Multiply 490 times 10, and you are going to get your work because the height was 10. 490 times 10 is 4,900, and work is in joules. So we figured out the amount of work just by understanding and knowing that, all right, if we know the mass, we can calculate that mass and turn it into work. Remember, work I'm sorry, not work, but weight. Weight is the force of gravity as well. So by finding the weight, which is his mass times the acceleration of gravity, we solved for the force of gravity and we plugged it in to the force for our work equation. That's how we solve for it. Now, if Geppetto's mother shakes the tree and Geppetto falls out, what is final velocity of Geppetto when he hits the ground? Ooh, consider potential and kinetic energy. Wow, this is a really good question. I like this. Now, we know that Geppetto up in the tree has a certain starting potential energy and kinetic energy, doesn't he? And also, when he falls and hits that ground, he'll have a certain final kinetic energy and a final potential energy. This is called the conservation of energy. Now, at the very height of the tree, he's not moving, so there's no kinetic energy. Kinetic energy is 0. And as that boy hits the ground, Geppetto hits the ground, he won't have any height, so he'll have no final potential energy. So this really means that his initial potential energy at the top of the tree would be equal to his final kinetic energy. And if we break that down, we know potential energy is mass times gravity times height. And we know kinetic energy is 1/2 mass times velocity squared. The only things we have to pay attention to is that the potential energy is the height initial, and the velocity is going to be the final velocity because it's kinetic final. So I think what we're solving for is this final velocity right here. So can we plug into this equation to solve for it? Sure. We know the boy's mass is 50. We know on planet Earth, acceleration is 9.8. And we know the boy's height is 10 meters off the ground. We also know 1/2 times the boy's mass again is 50. And we don't know velocity final, but that's what we can solve for. So look at that. We actually have everything we already need. If I multiply the left side, 50 times 9.8 times 10, you would get 4,900. Now remember, 4,900 is the total starting energy Geppetto has. But it's all potential, but when he falls, that's going to convert into pure kinetic energy. So this side of the equation also has to equal 4,900. We know that, but since we have all the numbers besides VF, velocity final, that's what we're going to solve for to make sure that this holds true. So let's do that. 1/2 times 50 is going to be 25 VF squared. I'm going to move up my work just a little bit to give us a little bit more room. Let me change my color too so we can better see the work. I'm going to divide both sides by 25 because that's going to get my velocity final squared by itself. 4,900 divided by 25 ends up being about, I think it's 190 something. Yeah, 196. Now that I have that, velocity final still isn't alone, it's squared. So let's square root that. Velocity final ends up by itself, and what we end up with is about 14 meters per second. So again, this all comes down to the conservation of energy. The idea that the starting kinetic potential energy, what we call the total mechanical energy initially, ends up equaling the final potential and kinetic energy, which we call the total mechanical energy final. And oh my gosh, that should have been an E for energy. Anyways, total mechanical energy initial equals total mechanical energy final. All right, I need to learn how to write my letters better, E instead of I. All right, but that was the first side of your practice quiz. Go ahead and dive in, take a look at it. Let me know if you have any questions. Obviously, this is just supplemental help to help you through. But when you're going through this, you might be thinking, man, I didn't understand one step where it came from. That's good. Pinpoint that problem and ask that in question in class. That's going to help us pinpoint where is the issue. Is the issue of figuring out what equation to use? Or is the issue once you plug it in, is it just the algebra? Regardless, there's nothing wrong with being confused, but we have to know specifically where our weak spots are so that we can tackle them and get better at them. The more specific you can be about a question, the more it's going to help you and the more efficient your learning can be. All right, keep up the good work. I'll see you on the other side eventually if we make another video for the second side. Be well.